Hey everyone, we got Jason today presenting on zero knowledge machine learning. So yeah, take it away, Jason. Thanks a lot for joining.
Yeah, thank you so much, Andy, for inviting me. And as I said, please feel free to interrupt if we want to talk about anything in detail. Um, so I'm skipping my what is ZK slide because I think the audience knows better than me. But I can talk about why zk-ML. And so the big picture for me is what we're doing is we're enabling, just like anytime we're pulling computation kind of off chain and producing a verified proof of something and then putting the result on chain. We're doing that for machine learning models and effectively running those machine learning models on chain. Why would we want to do that? The big picture is that it kind of gives smart contracts or on-chain executions the ability to deal with ambiguity of any kind, to absorb data that comes from hopefully signed inputs or any inputs, and perceive what's happening in the world. So eyes to perceive the physical world, ears input data from Web 2 or from events, and makes it possible for new kinds of identity primitives to exist. So you can imagine a future where my identity, my wallet is like a semaphore contract or something, a voting thing that manifests many facets of my identity. And every facet of that identity, some of them might be tied to secret keys, but most of them are tied to models, machine learning models that kind of model what a human would do when they're deciding, am I me, am I, and what my intent is. And so if you imagine that future, you could just kind of talk to the chain as though you were invoking some sort of deity, and it will do what you do your bidding because it understands you are you. It can also be something we could use to let smart contracts exercise judgment. So if they have imagine, for example, a DAO that's contracted people to perform some activities, make an update to their GitHub or do take some action in the world. You could have a smart contract that can make a judgment as to whether that action was performed correctly, or sort of in a more simple way, whether, for example, a news story came out that told you who had been elected Speaker of the House and you wanted to pay off based on that. And making sure we have some sort of method to create a permissionless, unstoppable on-chain AI, Skynet, whatever. So the project that we've been working on is called EZKL. It lets you take a model that you've built in PyTorch or TensorFlow, export it as an Onyx file, which is just a protocol buffers format for storing a completed model with fixed weights, and then turn that model into a circuit. So you can create a proof and verify it at the command line. You can export or create binaries that are, or sorry, bytecode that would be used for EVM application. And hopefully soon we'll be able to do some WASM stuff. It's a different execution environments. We're adding a lot of different nodes and layers. As you can imagine, there's often you have to put some thought into how to implement a particular function, because we're not taking a low-level VM approach, we're taking kind of a high-level approach. So we have to think a little bit about, how do you implement softmax, or how do you implement, ReLU or whatever. So that gets easier each time we iterate on it, but it still requires thought, which is actually really part of the fun of this, is because you're producing, you get to re-implement all the stuff from machine learning for the last 20 years. At high speed in a different computational format. Performance is steadily getting better, both because the upstream, we're using Halo 2, is getting a bit better, and also because we make some small, turn some dials, and the performance improves, memory goes down, time goes down, or we understand the trade-offs better. And that said, generally we're focused on making something that's kind of feature complete, that can at least load and run models slowly, rather than optimizing or hand optimizing any particular model, because we want to get to a place where someone can work with this exclusively from Python. They can live in a Jupyter notebook, and they can produce proofs and bake circuits and deploy things on chain. And it's open source, Apache license. Just an example of the kind of thing that might happen. So this is, you write a forward function, typical in PyTorch. It can take in tensors that have a shape that's defined at runtime. You can tell it, you can do different kinds of algebraic expressions, combining things, and then run it through to create an Onyx file, and then the Onyx file will be interpreted by EZKL and turned into a circuit, all at runtime. And we had to do some sort of, if you're familiar with Halo 2, Halo 2 doesn't really like that, so we had to do some kind of dirty tricks to get Halo 2 to accept more runtime configuration. And the basic usage is something like, you can do the table, which is just say, lay out the nodes, but don't actually do anything with them. Mock proofs, full proof, prove, verify. And then there's a bunch of parameters. Actually, not even listed here. Scale, which is, we're using a fixed precision representation right now, although that may change. Bits, which is the number of bits used in lookup tables. So nonlinearities are all modeled as lookup tables, and we can control with the precision. How many rows we use in the matrix. Separately, also we can control the number of rotations that are used. So you can sort of dynamically lay out each tensor depending on those parameters, and some other stuff. So this is an example of table. So just saying, okay, I have a layer, which is just a feed-forward layer. So it's just a matrix multiplication followed by a ReLU. And so this is how it would get laid out. You can do a full proof, which takes as input a model, that's the -m, and a data file, which is a JSON file that tells you what the floating point inputs of your model should be, and then it quantizes and produces proof. And that's a proof you can verify, also with the command line. Let me talk a little bit about kind of the timeline of how this has evolved over the past 6 months. So in July, as part of the summer 0xPark stuff, we're first able to get MNIST into a snark, zk-snark, using these non-linearity lookups, and then built in the stuff like EVM verification we're using the PSE fork of Halo 2. And then we sort of did a lot of refactoring, turned everything into real tensors, added the ability to read Onyx, and make more general purpose quantization. And we've done a lot of work throughout on improving developer experience, documentation, and just we're trying to spend a lot of time thinking about how can we make this easy for people to build proofs in. I think our use case is very different from Scroll in that we don't have a specific circuit that we want to run really well. We want to make it so that people have an easy time generating arbitrary circuits from Python code. And then we moved on to adding more operations, just nice displays and this sort of multiple commands at the command line, abstracting the proof system and general EVM, reducing the number of passes and quantization. We added a tolerance thing. So one of the things we do is enable you to say, well, this was a floating point computation originally, there's a floating point witness originally. The result that you get when you use the quantized fixed precision version may not be exact, so you can have a little bit of tolerance. If you're off by a very small amount due to numerical error, that will still be a valid proof. And we've been continuing to get the memory usage down by turning various dials. We find that the circuits we're producing are kind of different than the ones that a lot of other people are producing with Halo 2, and so we get sort of different results than you might expect by turning the dials. And we've been working on something called Fusion, which is to combine operations into bigger and bigger gadgets. And over the holidays, we did the painful thing of turning on the lint in Rust that will reject your code if every struct and function is not documented and fill out all the documentation. So going forward, I think we're working a lot now on more nodes to be able to support some of the examples we're interested in, and in building in some ideas from recursion and composition, hopefully, over the next couple months. Let me stop for a second and see if there's any questions before I continue with the next bit. Okay, so the next thing I want to talk about is, okay, the name of the conduit is kind of the idea of that we should have a pipeline for zero knowledge proof that might begin with some kind of input, whether it's signed data or something else, or the output of something else or something from blockchain, produce a proof, verify that proof and take some action. So ingest, proof, verify, act. And that has lots of applications, but it's a somewhat complex pipeline that we have to do some thinking about how to arrange our activities so that these work. And so a typical situation will be we take some data that's been signed or somehow attested to on the web or on the blockchain. We check that the data is valid and its provenance is good. We run a model, maybe it's a text model, maybe it's an image classification model that's making a decision, who won the Speaker of the House election, whatever. And then we verify that proof either in the command line or on chain. And of course, we take some action. At a minimum, that action might be just recording the results so that it can be used in another pipeline. And on the authenticated content side, it's we're in an interesting place where there's a sort of an increasing push to create signed data for consumption, either by zero knowledge proofs or by just people who are concerned that, hey, we're now in this world of generative AI where we really can't trust what we see unless we see it with our own eyes, right? So one solution, or partial solution to that, is to ask people to sign the images and data they create such that even if you don't know that it's true, you at least know who's staking their reputation on it. So there's been some efforts on that going for many years, but I think are starting to pick up because of the threat from generative AI. And that's as different as signed endpoints, signed HTTP endpoints, which is sort of a very generic solution, to something like a camera produced by Sony that signs the images that it creates. And then there's transitional technologies where if the producer of the data isn't signing anything and you'd like that signature to exist so you can check it in your ZK proof, then you can have a third-party notary like Chainlink or Lit or the TLS notary project that will create a separate signature, third-party signature that agrees that they saw that data. But in general, it's kind of a political problem. Something like Let's Encrypt, I think, or something like the push to HTTPS that we need to push industry-wide. Lots of people have promised to do it, and not some people are actually doing it yet. So then the place we're at with the project is that we're kind of, I don't know if you know this sort of very old meme, ontogeny recapitulates phylogeny, meaning that evolution kind of, or the way that a baby develops looks a bit like the way that the ancestors developed. And so we're in this loop now where what we basically do is someone sends us a model that they would like to run, or we download a model from some online zoo. We figure out what problems that models cause. We maybe have to implement some new nodes or some new gadgets. Maybe it's pushed the limit of what we can do in terms of size or our quantization strategy, our fixed point strategy. So we fix those problems and then we repeat. And each time we do this, of course, the system gets a little bit more general. And eventually we'll sort of move from what I would call almost like an enterprise approach, where we're dealing with individual customers that want to run models, to more of a self-serve approach where it works most of the time out of the box. On the scaling side, we sort of have 5 tools at our disposal. The first and easiest is kind of just optimizing the way we're laying out our circuits, maybe some small changes to the way Halo 2 works, stuff like that. There's still a lot of gains to be made there. Aggregation, which is to use aggregation proofs where a similar structure proof can be combined and verified once. that kind of lets us split proof generation horizontally is the image that I use. Hopefully recursion will be something we can make use of soon, although it's being a bit slow in terms of getting into Halo 2 directly. But that would be beautiful because we already have this kind of graph or layered approach. If we can use the output of a separate layer as the input of the next layer, check the proof and continue, then any memory issues that are causing scaling problems go away. And it's just a matter of patience and how much money we're willing to spend to produce the proof. A lot of computation. I think more exciting is kind of this direction of fusion and abstraction where we say, all right, we have a very high level understanding of what we're trying to do. This high level understanding comes from the intent expressed by the person who wrote this Python code, right? They want to do matrix multiplication or they want to do some big operation. We don't have to go drill down and perform all the individual additions and subtractions, arithmetic. If there's a proof, if there's an argument available that can deal with the whole operation, for example, a matrix multiplication argument or a NTT argument. So those give us a chance for a much smaller overhead. In a sense, like lookup is an example of that too. And then finally, I think that it will be wonderful in the future if we can use different proof systems that are better suited to different situations and compose them. So there's kind of a matrix of input, proofs and verifications that can be done in different systems that's slowly being filled in over time. Right now, that there's not a lot of interoperability there, but we can imagine that as a part of the future for ZK. This is just about aggregation. Aggregation typically producing lots of easy to make, hard to verify proofs, compressing them on a big server that might use a lot of RAM, and finally producing a easy to verify proof. And this is particularly important for stuff like zk-KYC, where we want to be able to run the initial proof on a device. Its most important characteristic is that it preserves privacy. It doesn't have to be easily verifiable, and then we can do the work to make it easily verifiable so it can be used on chain. As I was saying before, one of the advantages we're finding of using Python, PyTorch, TensorFlow, Onyx is that it gives us this very high level representation of what our circuit is. So unlike a lot of proposed intermediate IRs that kind of deal at the level of polynomials, this is at the level of matrix multiplication or sort of bigger operations. It's also nice because it is a circuit notation, right? So TensorFlow, PyTorch produce a circuit, a computational graph. Typically doesn't have branches in it, and it's already a paradigm people are comfortable with, and so there's not a lot of impedance mismatch between a network they baked and a circuit that we can run in a proof. And so that means that we have a little bit easier onboarding for people who are coming from AI, ML, data science, used to thinking about this kind of a circuit for their pipeline. And we're sort of like to get to a point where we have a computational graph, which is fixed by the end user, and they never have to touch it again once they've baked it into an Onyx file. A compiler like EZKL that fuses these operations into supported arguments and then kind of implements it in Halo 2 or wherever Halo 2 is going, or more generally, maybe some other proof system, Supernova, Plonky2 or whatever. And that those things can be relatively abstracted from the end user who just needs to care about what do they want to do as a data science operation. And I think we're in this world where over the next 3+ years, proof systems are going to be very, very fast changing. In fact, they're the lookup papers alone are coming faster than anybody can implement them. And so we think of those something more like a compile target or modules that we can insert and the cryptographers can deal with without having to expose it to the end user. Just changing the cryptographic backend, but using the same high level graph description because we have a deeper understanding of the intent of the end user. And hopefully we'll just see performance improvements, maybe some version markers or something. Right, so on-chain verification, of course, important to take that action at the end of one of these pipelines. And that sort of results in what I call like a trustless on-chain data feed. Anything that we want to get on chain, whether it's price information or it's a strategy or it's data about the physical world, can run through this kind of a pipeline and feed into the next pipeline. Okay, so since this is a very technical audience, I want to talk a little bit about, and since Scroll also uses Halo 2, of course, a call later on today. I want to talk a little bit about Halo 2 and the future that we're hoping for Halo 2. So I think Halo 2, and one of the reasons we selected Halo 2 to build on is that it really has the potential, one of the few candidates, to be a meta system or meta proving system for ZK. I think of it as kind of probably proof systems will evolve something like the way that machine learning did, where there's kind of a couple of big libraries, TensorFlow, PyTorch, maybe scikit-learn, or maybe you can even include statistical software like R. But there are a couple of big systems that are composable and that are used for both production and experiments. And so I think Halo 2 has a hope to get there. I think we need something that's extremely modular. And modular in the sense both of arguments. So, if I want to be able to add a sum check argument, or I want to change my lookup argument, those things should be something we can add into the system without breaking it and not have it without forking it, hopefully, or at least with that maybe as a plugin or something. We'd like to be able to change the commitment schemes, which of course we can already do, but maybe there are other commitment schemes that we'd like to explore. So when people are working on Fry, for example, in Halo 2. Better support for aggregation for recursion and composition. I don't know if that could be something that we make into something that's native in Halo 2, or it sort of has to live a layer above that, but hopefully it would be at least inform the way we design the system going forward. I think as important and analogously to PyTorch or TensorFlow is that those systems support varied execution environments, right? You can write one program in PyTorch or TensorFlow, and you can run it on your phone, you can run it on the TPU, you can run it on NVIDIA hardware, all kinds of execute, or on your CPU, right? You can run on different execution environments. You don't really have to care about it as a user, other than looking at the speed. And I think we're going to, and memory requirements, and I think we're going to get to the same thing where we'd like to be able to run our proofs in Symposium, or run them on the phone, or run them on, FPGAs, GPUs, whatever resources we have available. And that's that last part of it, as people like Enganyama build hardware that is tuned to doing MSM and stuff, that it will be critical for that kind of stuff to be supported in Halo 2. That's kind of free speed improvements that we will all get if we can get that kind of stuff built. So I'm sure we'll talk about that later. One other kind of technical thing that I thought would be interesting to talk about is quantization and floating point and fixed point. So, okay, so just to sort of give the background of how we're approaching the problem. There's lots of different ways you could do it. So one extreme thing would be you use a field element to represent a bit, and then you just do bit by bit floating point arithmetic. That would be possible, but very expensive. The other sort of extreme is what we're basically doing, which is that we're taking 32-bit floats and we're quantizing it to a field element that's related but different to something which happens a lot already in machine learning, which is quantizing to int8. So they quantize the int8 for performance and size of the model, but they do it in a little bit different way, where kind of they always can fall back on having the weights still in the system. The weights and the activations, the floating point ones, have kind of a reality to them that we don't really have available when we're constructing a proof. So that's the sort of inspiration that comes from the way that they've done it, but it's not exactly the same. So what we're using is sort of a fixed point representation with a 32-bit integer and a scale factor. And for any given fixed model, you can do this whole quantization process in a manual way. you can take shortcuts and you can get a lot of optimization. But we're trying to build a compiler that doesn't know in advance what the circuit's going to be. And so we need to develop kind of an automated quantization strategy. That's been surprisingly tricky, but is also pretty fun as kind of like a research project. There's different ways of looking at numerical errors. It's a good chance to kind of review your numerical analysis that you thought about in computer science or mathematics. And right now we're taking an approach that I would say is almost like type theoretic, where we keep around a denominator for each value, which is defined at circuit creation time. And that works okay. We're also look at a statistical approach where we try to gauge the range that different activations will possibly occupy at the circuit creation time. And also thinking about ways of doing a partial or even a full floating point implementation that is cleverer or more sympathetic to the field element structure of the polynomials than it would be to do it bitwise. Maybe not bitwise, but something that's more like a generalization of what we're doing with scale and integer representations. But anyway, this area for most efficient quantization is a really fun one to think about. There's already been lots of work, for example, in doing things like packing multiple values inside of a single field element. That wasn't optimal for our use case, but it's an example of the kind of clever stuff that could be done. And one other comment I want to make that's a bit related is sort of abstraction. So as we're building this, as I said, the goal is to make it so that it's very easy for people who are coming from a Python or an AI/ML background to build computational graphs and to create proofs and verify them. And we're also trying to make it as an open source project, something that's easy for people to onboard. So we've had a lot of contributors that have successfully contributed, and even more that have tried to contribute and ended up passing, partly because there was some complexity in the system that really stuck them. Easier to add, for example, operations by having to change less code or choosing better abstractions in the Rust code and documenting it better. A more general version of that same problem, I think, is really true in ZK. So if you talk to people who build cryptographic applications, a lot of people, for example, understand signatures. They understand ECDSA signatures or BLS signatures. They have a good mental model of how that works. And they can build a great big complex system that's entirely constructed of this thing signs that thing and this thing signs that thing, and you have a tree of authority or public key infrastructure. And so it's a very comfortable abstraction. Now we could replace most of those systems with a ZK-based system, since ZK is a generalization of the digital signature. But part of the reason that that's hard is because it's almost like we have too much power, right? I like to think about it as software developers, right? If you think about a sculptor, right? If you hire a sculptor to make you a beautiful sculpture, and he just hands you a block of marble and he says, "Hey, this is a block of marble. This could be any statue you like," right? I think that when we hand someone too general of a tool that's basically just a Turing complete computer, and you say, "Hey, you can do anything you like with this," it's actually not very helpful. It's like the sculptor handing someone a giant block of marble instead of a finished sculpture. So I think we have to cut down a little bit and think about what are the nice abstractions that we can create. They might not be as powerful, but they're easier to understand and they're easier to compose. So I think a lot about that in terms of building zero knowledge stuff. What's the next generation of kind of composable units? And related as well is how do we support proof system modularity at the user level and the intermediate levels? So as we get to a Halo 2 or a broader ecosystem that supports different commitment schemes and different arguments and everything else, how are we going to represent that to the end user? Maybe we're going to hide it. And how are we going to represent it internally such that the system, in this case, I mean, in EZKL, how can EZKL have in the background, how can it have a representation of the computation that we'd like to do such that we can add and subtract arguments, and it will use them if it can. So that we're just at the beginnings of really thinking about that. Let me pause for a second before I talk about applications and see just if folks have any questions.
So for this abstraction layer, are you kind of envisioning like a layer, like a developer layer on top of Halo 2, where like you have these like higher level operations and you just call these higher level operations and it goes and like writes it lays it out in a Halo 2 circuit? Is that what you kind of mean by this
Yep.
abstraction?
Yeah. Well, I mean, I'm talking about a couple of different things, but one of them, right, is that kind of abstraction. For example, the gem node, the matrix multiplication node, right, or matrix multiplication plus shift node, or matrix multiplication plus ReLU node. That thing, we need to keep it around as an object, so that we can, when we have the chance to, we can swap out smarter underlying pieces. It's a sort of a typical compilation problem, right? And it's like your compiler should be smart enough to use hardware instructions if they're available, for example. It's a lot like that, and fall back on software limitations if it's not. I think it's a similar problem for ZK stuff, where hardware implementations are like having a custom argument or a particular argument that's suited to that. That's like having a fast, floating point or hardware arithmetic or something. And if we don't have that, we fall back to the soft float implementation.
Yeah. And then I also had like some question. I was wondering if you could elaborate a bit more on kind of like the quantization strategies. Like, I know you made a distinction between like manual quantization and automatic quantization. Like, what are the strategies for manual quantization? Like, what does that actually look like? How do you translate these floating point values to field elements?
Yeah. Okay. So typically, to translate it, you take the floating point. I mean, so the basic idea is simple. So you take you take the floating point value, you multiply it by 128 or 256 or 8 or whatever, and then you keep around that denominator. So you represent, 10, or you represent one, let's say, point, whatever, 0.1 or something as like point, or as 12, or sorry, yeah, 12, right? So 12 out of 128 is approximately 0.1, right? So if your input was something like 0.1, then you get something like 12. And then when you can multiply, and you have to keep track. Okay, now your scale went up. So your scale was 7 log 128, and now it's 128 times 128 if you multiply two of those values together. So for example, you're taking a dot product, right? This typical situation, we have a dot product. Both of them are quantized at the 128 level or 128 scale, and then the output of that will be at the 256 level, or it will be to the 14 level, right? And it'll be all those values, the integer values multiplied by the other integer value, and then they're added up. And the multiplication can cause overflow, kind of, and the addition can further cause overflow. So you have to worry about, if I only have certain range of values in my lookup table that I can apply nonlinearity to after this, then I have to either statically prove that I can't have a overflow, or I have to kind of statistically hope, right? So they say that in the examples that I want, most of the values are between 0 and 1, right? I'm not going to run into a floating point value that's 1,000 in my input. And so I feel comfortable that as long as the dot product is no more than 8 or no more than 100 or no more than 300, whatever it is, I won't run into overflow. So manually, you can kind of just run the circuit and be like, oh crap, I got overflow. And then you make an adjustment to fix that so that on the examples you care about, you won't get the overflow anymore. But if you're doing it in a compiler, you sort of don't have the luxury of running those examples and then adjusting. You have to sort of try to make those decisions a priori. how many things can I get away with? When do I have to start tiling, or when do I have to do whatever other tricks to get around the scale problem? When another example is that in doing that, right? So you do the dot product, you multiply two things together, the scale has gone from 2 to the 7th, 2 to the 14th. Now, before you feed to the next layer, you want to bring it back down to 2 to the 7th, right? And so to do that, what we typically do right now is to insert a division layer where we use a lookup table to divide by 128, and then sort of requantize. And then that question of where do you insert the division, again, kind of depends on the particular circuit and the types of inputs and the types of outputs it gets. Another example is you can have convolutions or matrices that are balanced or not balanced, right? So like you can have one that, for example, a convolution such that the sum of all the weights is 0, right? That's better for protecting against overflow than one where all the weights are positive. That's not an issue when you're working with floating point numbers, but it's a huge issue when you're working with these kind of fixed point representations.
Okay, yeah, that sounds complicated.
Yeah, it gives you a flavor of the kind of problems, right?
Yeah. So it sounds like the manual thing is like, kind of debugging manual evaluation or inferences and checking if there's overflow, and if there's some overflow or something, adjusting how you're adjusting your quantization strategy such that you avoid those issues or something like this. I see.
Yeah, exactly. And then you try to take that intelligence and bake it into the compiler.
So that it's general, yeah. Cool.
Yeah, so that it's more general. Yeah, that's the iteration there, which is fun. I mean, I think there's a lot of numerical analysis. Some of it's even almost like a lost art, but that helps with this stuff. But there's also kind of likely to be a nice algebra of these objects that might emerge and be useful in making this kind of computation, where you keep not just the number around, but a little bit more metadata. You understand how the algebra of combining that metadata scale and maybe some statistical properties.
I have a question, I guess, about the abstractions. You're using Halo 2, and you were saying you think it could become, more standard and extended further. Do you think that the Halo 2 abstractions are at the right level in terms of, I know they have like these chips and gadgets, and then there's sort of a library of gadgets and chips. Do you think that is like the right API, or how do you like?
Yeah,
can you talk about what you're imagining in terms of abstractions, in terms of what's exposed by the Halo 2 API currently?
Yeah, some of what I'm talking about. So I think the gadgets and chips stuff makes sense. I think we've gone a little bit different direction, and I know some other folks have also gone a different direction, right? With like kind of a main gate strategy or managing the layout ourselves. So I'm not sure that abstraction is going to be the long-term one, just because it seems like people tend to not use it. But mostly I'm talking about is something that's orthogonal to it, in the sense that I want to be able to abstract, at least on this slide, right? I want to talk about abstracting the argument itself, which is a little bit higher level. Abstracting the commitment schemes, which is already sort of something that's available in the forks, and figuring out how to, support this other stuff, recursion and things like that. So we're needed to build a higher level of abstraction that's on top of Halo 2 in order to do what we want to do. But this problem of how do you make Halo 2 itself a meta system that can plug in different arguments and different schemes and execution environments is another kind of abstraction that's more like a typical code engineering refactoring type of abstraction.
Yeah, I noticed that in some projects, Scroll also hasn't been using some of the like the chip API that Halo 2 exposes. Can you just like shed some light on why you decided to build your own abstractions, or like, help explain what you didn't find correct about that one?
Hmm. Um, so well, okay, so it may be that I didn't fully parse that abstraction myself, but for us, one of the main issues throughout is Halo 2 is not really intended to produce circuits at runtime, right? Um, we need to produce circuits at runtime for this application. And so the way in which we want to compose the parts is a little bit different.
Okay, thanks.
Yeah, yeah, that's the best answer as to what guided us in the direction that we ended up going. Yeah. Okay. So the last bit I'll talk a little bit about is just the applications that we're excited about. Some of the applications we're excited about for zk-ML. The thesis is that zk-ML is some kind of table stakes for chains in the future. And a lot of that is about identity, the thing I opened with, where if you want to produce a notion of identity, and which I mean kind of the ability to authenticate yourself and take an action, that is not kind of only dependent on keeping your 12 words or your 24 words secret, not dependent on kind of the vulnerability to loss or theft of a secret, then you either need to kind of delegate or do some kind of NPC type thing, or you need this kind of full identity solution, decentralized identity solution, that is better at recognizing humans the way that your banker would recognize you, or your relative would recognize you, or your friend, right? I feel like the fact that humans can meet each other, hang out for a couple hours, not see each other for 2 years, and still after that 2-year period, you can authenticate, oh, this is this person and this is what they want. The fact that humans can do that, but our blockchains can't do that, is kind of a purely technical problem. And I think for kind of mass adoption, it's where we really have to solve a lot of different approaches to doing that. But obviously, I'm biased. I think that the zk-ML is going to be an important part of that solution. Relatedly, I think that the Oracle problem of just getting data, arbitrary off-chain data on-chain, the way to do that at scale is not to have, say, a network of nodes that together agree that they saw the same thing and play some crypto economic game that penalizes lying, but to do this trick where we say anybody can download a piece of data, check the signature, run the model, and upload the result, and everyone can trust that the computation they did was correct, and it has sort of the same validity as the source of trust, whoever that someone said it. Five out of 10 news organizations, or 5 out of 7 news organizations published an article that said so and so won the Speaker of the House, so we should feel confident that that was the result. And because of this ability to say, now smart contracts can act as smart judges, interpreting ambiguous events. Right, the traditional contracts, legal contracts, together with the legal system, is good at dealing with ambiguity and reflecting intent. And right now, we can do kind of extremely precise, but not necessarily accurate smart contracts, and we'd like to be able to do ones that are sort of both precise and accurate. So I mentioned zk-KYC. You prove that a person matches an ID, and that ID is not sanctioned. This is not a regulatory compliant KYC right now, but the point is that it's enough that it might prevent something like the sanctions that hit Tornado Cash, or it might prevent, keep enough bad actors off your system that your system doesn't become a target for regulatory action or other negative results. And so that, I think, is interesting, and it kind of makes ZK a way to increase your adoption. I mentioned also prediction market applications. So, you do something like classify text into a few classes, if something is possible with very small models. Constructing a smart contract that pays off if, say, a news story, a hurricane of a certain intensity hits, or a new code variant, whatever. And again, anyone can download the story, run the model, and submit the proof, and everyone can trust the result. Another thing that's sort of interesting to think about is something like fraud, where when a contract is hacked, usually it's fairly easy for the humans to, during the hack or retrospectively, say, oh, that was something we didn't intend. That was not the intent of the contract, right? It was according to the letter of the law, but it wasn't the intent. And if we'd like to add that ability to check intent, kind of gut check, to our smart contracts, then what we're asking for is some kind of a zk-ML fraud check that says, okay, this is an anomalous behavior. Maybe we should escalate it in some sense, or block it, or slow it down, whatever action we want to take. Another sort of gimmicky way of saying this is that we can maybe actually put the A in DAO. So right now, a lot of situations with DAOs are that humans make a judgment, they vote, and there's a multi-sig where the signatories take the action that the humans reflects the humans' judgment. And this is something where we could replace that entire process with truly truly on-chain AI automation. For example, that someone performed according to a contract to write some code or make a web page or whatever. Some non-blockchain applications might be something like improve the performance and unbiasedness of some model that you've committed to ahead of time without having to reveal the parameters. For example, there are a bunch of laws coming out with respect to the models that are being allowed to be used to screen resumes, and you could prove that your resume screening model was fair without revealing your secret sauce. Someone like the TSA could prove that they're being selected for additional screening was done in an unbiased way. Another example, before I go on, another example that's a little bit like this is kind of the DeFi application where you say, well, I would like to commit to a model that runs a certain portfolio rebalancing strategy. I'm not going to reveal my secret sauce, but I can prove that I've run that model and these are the results, and that's better than sort of trusting someone to go off and do that on their laptop and then upload the results. Another example is that you could combine it with something like MPC. If you're able to produce a zero-knowledge proof in MPC, a scenario would be something like a patient that wants a prediction, like the chance of developing a genetic disorder, but wants to check anonymously and choose whether and who to reveal that result to. And on the other hand, models for a lot of public health or a lot of health models might be trained on data that can't be publicly shared, for example, because the people that went into it didn't consent to do that. So those people have passed and there's no way to obtain their consent. And then the model has to be private to the model owner, the data has to be private to the patient. And so you could do something where the model owner and the patient proof inference together in MPC. Reveal the outcome without either having to reveal their respective information. Another sort of combo operation would be something like differential privacy, where it's the data that's kept secret and committed to publicly at regular intervals. You have a server that creates differentially private marginal summaries. You hand those noisy summaries out, and people can prototype their analysis. They decide a final model and they send it to the owner, and then the owner runs the model in ZK on the real data and returns that to the client. Maybe it's just a p-value, and they can prove that the real data matches the commitment was used to create that marginal summary and produce the return result. Okay, so that's all I've got. Still here for questions. I know it's locked for longer, but I can.
So I have a question about the O and an X format.
Yeah.
Is that a thing that different like numerical platforms essentially like compile to or like generate like an IR from, kind of like you have your PyTorch computation or you have some like R script that you wrote or something, and like you generate this computational graph like data structure from that essentially?
Yeah, it's basically a representation um, of the model graph. So, for example, it'll say it has all the constants baked into it usually. So it'll say, okay, I have a constant which is this matrix, and I have a constant which is this vector, and then I take the input, and then there's a node, and the node is I'll take the input, whatever the input is, multiply it by the matrix, add the bias,
Yeah, and you get some
and that's
true
the output of that node. And the next node is maybe a ReLU, and literally in the file, it just says ReLU. This is the input, this is the output. So it's a bunch of named objects. It's kind of minimal in the sense that it doesn't have shape information always. So you have to do some amount of inference at runtime in order to decide how to actually construct a circuit from it. But it's basically the same as if you create the model, if you have like a subclass to your neural network and you build a model in PyTorch or TensorFlow, it's basically that, a format recording that information, your instructions rather than what it is. That makes sense.
Is that a thing that's like only common in like ML stuff, or is it more widely used in like numerical software as well?
No, it's really just for neural networks.
Ah,
Yeah.
cool. Right.
I was wondering if you could share just like current benchmarks. I'm just wondering like what types of models are currently feasible in terms of like circuit size and proving size. Yeah, like what the current state of that is, and where I
Yeah,
know you
that's a
said
good question.
there's rapid improvement, but I'm just wondering what the current state is.
Yeah, I'd say kind of models on the orders of models on the orders of hundreds of parameters, super fast and easy. Models on the orders of tens of thousands of parameters are doable with the compiler. Models on the order of millions of parameters probably still require manual tuning.
Wait, sorry, manual tuning, are you talking about like the quantization part again?
Yeah, I mean, it's, in other words, like you can go do one that has 3 million parameters, but you probably have to sit down and write the circuit manually.
I see. I see.
Yeah.
And is that what is that because of like a lack of abstractions or a specific kind of like quantization strategy that is like
I'd say it's a combination of quantization strategy and just performance tricks.
So you would see that the like certain circuit that the compiler generates, like you could optimize certain ways, and you would like work on that essentially, or maybe
Yeah,
write it
like
from
be
scratch.
clever about packing it, or yeah. So that's, I should have better, but maybe I should start publishing some benchmarks. But we have some benchmarks that we run on our repository, but I don't know them off the top of my head. Mainly looking for practical, take an application somebody wants, because right now it's very dependent on the shape of the network, and for example, let's talk about the quantization stuff, right? So if you change the size of your dot product, you might start having it overflow depending on the weights of that particular network, and then you have to adjust your strategy, and that might be expensive. So yeah.
I see. Are there also like performance tricks that you can get by altering the architecture of the initial network that you're trying to prove, for example, like
Yeah, like sparsity, for example, should give a lot of. We haven't even opened that can of worms yet, but sparsity should help a lot.
I see, sparsity. Yeah, the thing I was thinking about was like the actual architecture, like whether you have like layers that have lots of neurons versus like having more layers, each with fewer neurons or something like this, kind of like a.
Yeah,
But
yeah. I mean, it's an interesting situation because model, for the most part, these models have been written and optimized with certain computer architecture in mind, right? They were written either to run fast on GPU or to run fast on phones or whatever, right? And essentially with the ZK stuff, we have a completely different architecture, which has totally different properties. So first order is kind of, we try to get the models people know about working, but even something that's optimized for efficiency may not be optimized for efficiency in ZK land, right? And
right.
maybe eventually we use models that are designed for this architecture, you know, but then we have to figure out how to train them and all that too, right?
Right. Like what are the like high level heuristics of like do you have a sense of what the high level heuristics are of designing a neural network system that is optimized for ZK inference?
Um, I think sparsity should be good. I mean, one of the heuristics is that all nonlinearities have the same price, and that's weird, right? So,
Because they're
ReLU
like
is nice for
lookups.
various reasons. Like ReLU is nice for reasons of derivative propagation, but it's also nice because it's very cheap to compute. But it's not cheap for us to compute, right?
Mhm.
Like it's a range check basically. So so taking a ReLU or applying a sigmoid function or dividing by 7 all have the same cost. And that's very strange. So, if we pack more into lookup, so, Barry has this thing, lookup singularity, right? So maybe in the future, that's all we'll use. We'll just use a whole bunch of lookups because that's getting really efficient, right?
Mm.
So for example, a model that leans heavily on the fact that lookups are kind of constant cost might be better in the long run. The matrix multiplication is not that fast right now, unless we put in a matrix multiplication argument and then it'll get better, that kind of stuff.
Yeah, speaking of that, like you briefly mentioned it earlier in the talk, but like things like Halo and or sorry, not Halo, Nova and Supernova. I was kind of like looking at it and it seemed very like kind of naturally analogous to like a kind of neural network where like you can have these series of matrix multiplications on some vector, and like to me that was like kind of analogous to like the different layers of a neural network. But then like the problem there is like you have to figure out how to inject like these non-linearities between the matrix multiplications. But I was wondering if you had any thoughts about like the supernova stuff, whether you see like a possibility of like having neural network inference implemented in something like supernova, if you've given
Yeah,
that.
I think I just think I'm optimistic about it. I don't understand it well enough yet to say whether it will work, but something I definitely want to try in the next coming months, basically, because it could be really great. Or the other thing to think about is whether there's some strategy that's good for floating point. So, for example, that might work well for floating point. Another thing that might work is these new lookup arguments, because they don't depend at proof time on the size of the table.
Mhm.
So if we can, so the extreme thing is like, oh, we can have a 64-bit table and we can just do floating point arithmetic, F32 arithmetic in lookups, because we can't have a 64-bit table, but maybe there's some intermediate thing we can do. Yeah, so I hope really unpacking the recursion, composition, and supernova type stuff will probably be important going forward. And I really hope we can do it without having to take a step away from Halo 2 and go to a whole other system. But we'll see.
Yeah. Cool. Does anyone else have any more questions? All right, I think we can end it there then. Thanks everyone for joining. Thanks a lot, Jason, for making it. That was a really
Thank you so much
great
for having me.
presentation.
It was wonderful to speak to you. Yeah.
All right, enjoy the rest of your Friday, everybody. Bye.
Bye.